Hi everyone, I'm Adrian Mong. Today we are going to present about experiment 6 and we are from group 1. So I will pass to the next presenter to present about experiment 6.
Hello, I'm Ahmad Yadin. I will continue for report summary. Experiment 6, Bourdon tube pressure gauge, is an experiment about calibrating a Bourdon tube pressure gauge using weights. All pressure gauges, no matter what type, must be calibrated from time to time to maintain its efficiency of giving the correct readings. The calibration is done by repeating the loading of dead weights and taking the readings of the pressure gauge and followed by unloading them and the readings of the pressure gauge is taken. The theoretical pressure is calculated beforehand and the error between theoretical and experimental results is evaluated and used to calibrate the pressure gauge. Now I pass on to the next presenter.
Now I will discuss about the theory part of this experiment. The Bourdon pressure gauge operates on the principle that when pressurized, a flattened tube tends to straighten or regain its circular form in cross-sections. The Bourdon tube comes in C, helical, and spiral shapes, although most gauges employ the C shape, which is the type of Bourdon picture here. When a gauge is pressurized, the Bourdon creates the dial tip pressure to enable pressure measurement. The higher the pressure requirement of the application, the stiffer the Bourdon tube needs to be, which means Bourdon wall thickness and diameter are key considerations for enabling the required tip pressure to traverse the necessary movement and thus facilitate pressure measurement accuracy. A standard gauge for an industrial fluid handling application would generally call for an accuracy range of 3 to 5% full scale. A Bourdon test gauge typically provides accuracy of 0.25 to 1% full scale. Next, the theoretical pressure in the cylinder can be calculated as the formulation before P equal to F over A. The measured pressure can be obtained from the reading of Bourdon tube pressure gauge. The percentage of relative error for theoretical and measured pressure gauge equal to pressure measuring minus pressure theoretical divided by pressure theoretical times with 100%. Next, pass to the next presenter to present about the procedure.
Hi, this is Ainalia and I will present for the procedures part. Okay, so first, the apparatus was set as the figure above. And next, 1 kilogram piston was put into the Bourdon tube pressure gauge after the test gauge reading was ensured to be zero. Then air bubbles inside the tube are removed by rotating the piston softly. Next, the first reading of pressure gauge is taken after the system is stabilized, and a dead weight was put on the piston. After the system is stabilized, the second reading of pressure gauge is taken. Next, another dead weight was added on top of the piston, and the third reading was recorded after the system is stabilized. Step 5 is repeated until the maximum weight of 5 kg is applied to the gauge. Next, the dead weight is unloaded from the piston one by one, and the reading of pressure gauge is taken for every unloaded weight. Next, step 2 until 7 is repeated for 3 times to get the average reading. Last but not least, all dead weight was removed and all the data was recorded in the table. Next, I will pass to the next presenter to present for the data analysis.
Hello, I will continue for the data analysis part. As usual, for every experiment, we have a few things we need to record and a few things we need to calculate using the formula given. This time, the table consists of mass, which is recorded in kilogram, which divide into two, mass added, and the total mass both in kilogram. Next is actual pressure in kilopascal, pressure exerted by total mass in kilopascal, the gauge pressure in kilopascal, which is experiment 1, experiment 2, experiment 3, and the average for loading, and experiment 1, experiment 2, experiment 3, and the average for unloading. And last but not least is the percentage error for loading and unloading. Now I pass on for the discussion part.
The first part we discuss is the percentage of relative error for the theoretical and measure pressure gauge. From the data analysis obtained, the percentage of relative error for theoretical and measure pressure gauge for loading is ranging from 13.7% to 35.3%, while for the unloading, the percentage of relative error is ranging from 0.6% to 35.3%. The high percentage of relative error obtained is due to several errors that occur during the experiment. Next, I'll pass to the next presenter to continue the discussion.
Hi, I'm Xing. I will continue the discussion about the source of error and whether to minimize the error. According to the results of the experiment, there are many errors that influence the outcome. As but is applied which can cause the friction. Next, the scale reading on the dead weight pressure gauge calibrator has an excessively large division. As a result, taking a pressure reading may be slightly inaccurate since the true value is not determined. Next, the apparatus is sensitive to salt and experiment. There were also various errors when carrying this experiment because the eyes are not perpendicular to the scale on the Bourdon tube pressure gauge. The errors may be resolved or eliminated in a variety of ways. We rotate the piston to remove air bubbles inside the cylinder tube and to reduce friction. To allow for a more accurate pressure reading, the scale reading should be more sensitive so that we can record an accurate value. When loading and unloading weight members should be more careful. Take the readings 3 times for a more accurate result. Then the multiple readings should be taken and averaged, and these readings could also be taken by several people. Next, we discuss about the repeatability and accuracy of this equipment. Repeatability means the same thing in the world of Bourdon tube pressure gauge as it does in the world of flow rate or other measurement instruments. It is a measurement of how often the pressure gauge repeats the same measurement over and over again while all other variables remain unchanged. For example, if all other environmental variables, pressure and temperature remain constant, the gauge would read the same PSI if exposed to the same pressure threshold. Next, accuracy is same as repeatability, equally and independently important in determining the quality of a Bourdon tube pressure gauge. If all conditions stay the same, the accuracy is a measure of how well a pressure gauge will replicate at the upscale reading on the downscale cycle. For example, a pressure gauge that reads correctly at 0, midpoint, and full scale during the pressure up cycle can read too high at the midpoint check during the pressure down cycle, but returns to 0 correctly. Next, I pass to the next presenter.
Okay, so back to me, Aina, for the conclusion part. So, in a nutshell, the aim of this experiment is to use dead weights to calibrate a Bourdon tube pressure gauge. Anytime the weight is raised, the gauge pressure is determined. The gauge pressure is recalibrated using the dead weights as the gauge accuracy deteriorates over time. The percentage error for loading is ranging from 13.1% to 35.3%, while for unloading is from 0.6% to 35.3%. The uncertainties in this experiment may be due to a combination of spontaneous and systematic errors during the experiment. The outcome of the experiment is influenced by several mistakes. As a result, the experiment must be repeated several times in order to obtain an estimated value. To reduce the percentage error, we must therefore ensure that all the equipment is in good working order. That's all from us, Group 1. Thank you.